Okay, let's talk some more about the memory now. So remember that the memory holds both the code for the program as well as data. Machines typically also break up the memory into other segments that hold different types of information or data. An example memory layout or memory map, as we've discussed previously, is shown on the right here. So we have one segment used to store the text or the code of the program, another for static data, and then we have some other segments which can change during the execution of the program. The stack, which we're going to talk some more in the coming lectures, typically starts towards the top of the memory and grows down, and the heap, which we won't get into in this course, but you'll see more of this later, is used to store more dynamic data. When we write our assembly programs, we can tell the assembler where we want certain data or code to be placed in the memory. We use the .text assembler directive to tell the assembler that all the instructions that follow this directive are going to be placed in the text segment, and the .data assembler directive to tell the assembler that we want the following information to be placed in the data segment. So let's talk some more about the memory in the context of an important high-level construct that we use, which is arrays. So you've probably seen arrays in high-level languages before, for example, in Python. Here I have some C code showing the usage of an array. So this first line here is declaring that I have an array of 10 integers, and they've been initialized to these values. In the following line, I'm doing an add, where I'm adding the variable h plus the 8th element of the A array and putting the result into G. So let's look at how this would translate to assembly. So first I need to declare this initialized data that's in the array. So we'll tell the assembler that we want some data in the data segment, and we can use another assembler directive, period word, to tell the assembler that we'd like to allocate some word length values in the memory, or 32-bit values. And here we can list the entire array separated by commas. We can also use a label so that we can later in our program refer to this data. In this case, the label will correspond to the first word in the data segment, in this case the 0, or more specifically the location of that 0 in memory. We'll then describe our text segment, or the code. So let's assume that our variables G and H are stored in the registers T0 and T1. T stands for temporary, and if you look at figure 3 within our cheat sheets, you'll see that T0, T1 are just other names for the registers X5 and X6. So now to get the value A8, or the 8th element, or more specifically the 9th element, because our array starts at the index 0, I'm going to have to load from the memory. And so I need to get the address for that location. Now remember, we have the label A, which translates to the address of that first piece of data in the data segment. If I used an li instruction, the pseudo instruction load immediate on the label A, put that into a register, that's going to give me the value 0. And instead, what I can do is use the pseudo instruction la, stands for load address. If you look at your cheat sheets in table 2 for the pseudo instructions, you'll see the base instruction here is going to be the add upper immediate PC, AUI PC, and an add I instruction. This will create the address in memory that corresponds to the label A. Now that we have that address in a register, we can use a load instruction to fetch the data at that location. But remember, we don't want the 0, we want A8, the 9th element in that array. So we'll do a load, putting the result in the register T3. The base address for that load is going to be the register T2, which is the address of the first element of the array. And then we're going to add an offset to get to the value we want. In this case, it's the 8th element. Each element is 4 bytes long. Our addresses for our ISA, the RISC-V, the RV32I, are byte addressable. So every address refers to a different byte in the memory. So I'll multiply 8 times 4 to get the offset of 32. This will give me the value of the 9th element of the array. In general, if I want to access an array or iterate over it, then I'll have to do similar arithmetic to calculate an offset from the initial element of the array, or I could also keep a register and I simply add to it an increment as I go through it. Okay, so now let's talk a little bit about I/O. So remember, as part of our basic architecture, we have the CPU, the memory, connected together by a bus. We also have a way to get information in and out from outside the machine, which we call input and output. So this could be, for example, connecting to things like the mouse and the keyboard or the display, or things like the networking and communications. Systems today have many different types of I/O, and this is especially true for embedded type systems. To support I/O, a machine can implement it different ways. Some machines, including the RAT that we previously used, use what we call programmed I/O. So there were two special instructions called in and out that are used by the assembler programmer to actually access these different input and output devices. Another approach that is more common nowadays is to use what we call memory mapped I/O. And the advantage of memory mapped I/O, unlike programmed I/O, is that we don't need special instructions and we don't have to actually change our data path or control for these instructions in the ISA, and instead can map certain locations on our memory to the different I/O devices. So now from the perspective of the programmer, all we need to do in order to access these devices is simply load and store from certain memory locations. And these are hardwired or hard-coded into the machine. This helps reduce the complexity of our ISA by having less instructions. So let's look at an example. Let's say that we wanted to write a program for our adder that will read in data from the switches on the Basis 3 board, complement that data, invert all the bits, and then output the data back to the LEDs. Okay, so in the first line here, we're using another assembler directive called the .equ, which is equating the symbol switches to the value in hex 11 followed by 5 zeros. In the adder memory that I gave you, this is the address, an arbitrary address that I chose to map the I/O for our switches. For the LEDs, they're mapped to 1108 followed by 4 zeros. Okay, so now in our text segment, the first thing we're going to do is get the address for the switches. So we'll do a load immediate and LI instruction from the label switches and put that into the register X6. Now to read the value of the switches, all we have to do then is do a load from that location. So we do a load into register X5 from the location 0 plus X6. To complement the switch data, for this we can do a trick of just XORing the value of the switches in register X5 with all ones. Now to write the value to the LEDs, we'll just do a store, but in this case, this is wrong. We don't want to write it back to the switches, we want to write it to the LEDs. So let's do an LI to load the value, put the value or the address of the LEDs into register X7, and then we'll do a store to that location to write the value, the complemented value of the switches to the LEDs. And then this program, as is frequently done in many embedded systems, it just repeats continuously. Okay, so this is a nice segue then to another really common set of operations or patterns that we see in programs, especially low-level programming that we do with embedded systems, something called bit masking. So frequently in these types of systems, we need to manipulate individual bits rather than entire 32-bit values. And so I've listed here 4 of the most common operations that you'll probably want to do. These include setting a bit, clearing a bit, toggling or inverting a bit, and then also checking a bit if a bit is set to 1 or 0. The trick here for each of these that you can think of, when you see the term setting a bit, you should be thinking the OR operation, because when you OR something with 1, it doesn't matter what that bit that you're ORing with. When you OR anything with 1, the output's going to be 1. So say, for example, we wanted to set the first bit of the register. We're going to OR that register, say it's X5, with a value that has all zeros in all the positions, because when I OR something with 0, it simply stays the same, which is what I want. I don't want to change the other bits, but I do want to force that least significant bit to be a 1, so I'll put a 1 in the least significant position. If I wanted to set, let's say for example, the 4th bit, then I would OR the register with the value that has all zeros in every position except for that 4-bit position, which in decimal is 8. If I wanted to clear a bit or force a bit to be 0, and by the way, this could be a single bit or all these could be multiple bits at a time, you should think of clearing as an AND operation, where I AND the register with a value that has 1s in all the positions that I don't want to change, because when I AND something with 1, it stays the same. And then for the bits I want to force to be 0, I'll AND them with 0. So say, for example, I wanted to clear the least significant bit, I would do an AND. But in this case, I'm going to AND it with the value that has all 1s except for a 0 in the least significant position, which in hex I could write as FFE, or in decimal, this is equivalent to -2. Remember, this immediate field is going to be signed extended automatically by the machine. For toggling a bit, you should be thinking XOR. So if I wanted to toggle a specific bit, I'll simply XOR that particular bit with the value 1. And all the bits I don't want to change, I'll XOR with 0. So this would toggle the least significant bit. Finally, if I wanted to check a bit, we can do this different ways, but most likely we'll also use an AND. But in this case, I'm going to AND, let's say I wanted to check the least significant bit. I'm going to AND the value in the register with the value that has all zeros except for a 1 in the first position. Now I can check the result and see if it's equal to 0 or not. So if the value is equal to 0, it means that least significant bit was a 0. If the value was 1 in this case, it would mean that the value in that least significant bit position was also a 1. So in this case, I can do a BEQZ, branch if equal to 0, to branch to a location where I do something if that particular bit was not set.